chapter 5.7 conclusion. Return for a moment to the problem of the superintendent who is considering hiring additional teachers to cut the student-teacher ratio. What have we learned that she might find useful? Our regression analysis, based on the 420 observations in the California test score dataset, showed that there was a negative relationship between the student-teacher ratio and test scores. Districts with smaller classes have higher test scores. The coefficient is moderately large in a practical sense. Districts with 2 fewer students per teacher have, on average, test scores that are 4.6 points higher. This corresponds to moving a district at the 50th percentile of the distribution of test scores to approximately the 60th percentile. The coefficient on the student-teacher ratio is statistically significantly different from 0 at the 5% significance level. The population coefficient might be 0, and we might simply have estimated our negative coefficient by random sampling variation. However, the probability of doing so and of obtaining a t-statistic on beta sub 1 as large as we did purely by random variation over potential samples is exceedingly small, approximately 0.001%. A 95% confidence interval for beta sub 1 is negative 3.30 less than or equal to beta sub 1, which is less than or equal to negative 1.26. These results represent progress towards answering the superintendent's question. Yet a nagging concern remains. There is a negative relationship between the student-teacher ratio and test scores, but is this relationship the causal one that the superintendent needs to make her decision? Districts with lower student-teacher ratios have, on average, higher test scores. But does this mean that reducing the student-teacher ratio will, in fact, increase scores? The question of whether ordinary least squares applied to the California data estimates the causal effect of class size on test scores can be sharpened by returning to the least squares assumptions of key concept 4.3. The first least squares assumption requires that when beta sub 1 is defined to be the causal effect, the distribution of the errors has conditional mean 0. This requirement has the interpretation of an effect requiring big X class size to be randomly assigned, or as if randomly assigned, because the California data are observational. Class size was not randomly assigned. So the question is, in the California data, is class size as if randomly assigned, in the sense that the expectation of u given x equals 0, or big E of u given big X equals 0.